So this is going to be a little bit technical, but do try to follow along. It's very, very important. Let's take a closer look at the action potential, or as it's sometimes called, the nerve impulse. The action potential is an electrical impulse that travels along the axon that is surrounded by a semi-permeable membrane that allows only certain ions to cross through it. Ions are chemically charged particles that are found inside and outside the cells. In its resting state, the fluid outside the axon contains a higher concentration of positive ions than the inside of the axon, which has many negatively charged ions. This resting potential was measured at negative 70 millivolts, or thousandths of a volt. So neurons do not stay in this resting state. Rather, they can change and do change when an impulse increases the positive charge inside the neuron to a certain threshold. The neuron becomes locally depolarized to a charge of positive 40 millivolts and fires an action potential, or a nerve impulse. The action potential travels along the axon to signal to other neurons. More specifically, during an action potential, sodium ions, their positive charges, enter the axon. After the action potential occurs, potassium ions cross outside the cells, and then the neuron must transport these ions to return to its resting state. This results in a refractory period, wherein the neuron cannot generate another action potential. This entire process, from start to finish, lasts only about 5 milliseconds, or 5/1000ths of a second. So one important point to make is that every time a neuron fires, it fires to the same degree or amount. It goes up to positive 40 millivolts. No more and no less. This is known as the all or none principle. Stronger responses involve simply more neurons firing, not individual neurons firing more strongly. So if you want to find out more about some of these technical details, you can find that information on some links that we'll post on the web.